Welcome back. Previously, we have discussed how we can find n factorial using recursion. So that's the pseudocode we have over here. It's interesting to note that we could have achieved the same thing. That is, we could have found n factorial iteratively as well. So that would be something like this. Let's say initially factorial is set to 1. And then we iterate from 5 to 1, and then we just keep multiplying. So initially fact is 1, and then I is 5, so this becomes 5 into 1, and then I becomes 4, so we multiply to this 4, and then this becomes 3, so we multiply it, and we multiply 2, and we multiply 1. So this over here also gives us 5 factorial. It's interesting to note that whatever we did using recursion could also be done using iteration. So this is an important thing that you should know. Things done recursively can also be done iteratively. Another thing to note when we compare recursion and iteration is that an advantage of iteration over recursion is that it does not use space on the call stack, recursion call stack, okay? So we have seen the recursion call stack, we've visualized it, it's something like this, right? We had all the calls over here. So when we solve the same problem iteratively, we do not use recursive call stack space. So therefore, you will see that in many coding interview questions, you can achieve a better space complexity with an iterative solution as compared to a recursive solution. So this is another interesting point when we compare recursion and iteration. Another interesting point, and let me make some space over here, when we compare recursion and iteration is that recursion has both an ascending phase as well as a descending phase. Now what do I mean with that? Again, let's first take a look at iteration to understand this in a better manner. When it comes to iteration, it only has the ascending phase. So this means that we go from I equal to 5 to 1 in this case, and we iterate from 5 to 4 to 3 to 1, 2 to 1, and that's it, right? So there is no coming back. Once we've gone from 5 to 4, there is no coming back to 5 again. But when you take a look at recursion, notice over here that once we have, like, again, let's take a look at the recursion call stack. So let's say we have f of 5 over here, and we have f of 4 over here, and we have f of 3 over here. Let's say f of 1 is popped out, f of 2 is popped out, and then we come back to f of 3. So let's say we are again in the body over here. Notice that we are again over here when we get the value, right? When we get the value of f of 2, we are over here, and we can do more things over here. I could print something, or I could do some other operations. So recursion has not only an ascending phase, which is what iteration has, but recursion also has a descending phase. So this is something interesting which we can use in different questions. So the bottom line is that everything that's done recursively could be done iteratively, and we have seen that iterative solutions have better space complexity. So why use recursion if this is the case? The answer to that is that solutions written in a recursive way are many times more readable and easy to write and comprehend, especially when it comes to complex questions. So that is why recursion is a powerful tool, even though it has some disadvantages, such as it using more auxiliary space. We have seen that recursion is nothing but a function calling itself until the base condition or the terminating condition. So the base condition tells the function when it can stop calling itself and then start returning. So that's what the base condition is all about. Now, the wrong way of trying to identify the base condition is trying to visualize the whole recursive sequence and then identifying when the function should stop calling itself. Especially, you will find this difficult in complex questions. Now there is a better way of identifying the base condition for a recursive solution, and that is by thinking of either the last valid input or the first invalid input. Okay, so there are these two ways. You can either think of the last valid case or the first invalid case. Now these two are pretty similar in that you could in some cases write either way the solution, or in some cases you will find that one of these is more easier to implement. But again, the point I'm trying to make over here is that to identify the base condition, don't try to visualize the whole recursive sequence, but rather just think of the last valid input or the first invalid input. Now let's take two examples to understand what I'm talking about over here. So over here we have two pseudocodes. So this over here is the pseudocode that we have seen to find n factorial, and notice that in this case the base case over here is the last valid input. Okay, so you can see that over here the last valid input is 1, and in this case we are just returning 1, and the function stops calling itself. Now we know that, for example, n factorial, or let's say 5 factorial for simplicity, is 5 into 4 into 3 into 2 into 1, and 1 over here is the last valid input. The next input over here would be 0, which is not valid, right? So at this point we have decided to stop calling the function and we are returning 1. So this over here is one way of identifying the base condition, and the other way over here is to think of the first invalid input. For example, over here we have a function that can be used to print the values from n to 1. Okay, so let's say n is equal to 5, so the output would be 5, 4, 3, 2 and 1. Now over here notice that the base case has been written as the first invalid input. So the last valid input in this case is 1, and after 1 we get to 0, which is less than 1, right? And this over here is the first invalid input. So again you could write this in the other way as well, like you could tweak this and write it such that the base case is based on the last valid input, but I'm writing it purposefully in this way over here to give an example. Now these two things are very helpful, especially in complex questions, to come up with the relevant base condition. Hey everyone, welcome back. Another important term that you will see with respect to recursion is the recurrence relation. Now the recurrence relation is the expression that talks about the solution of a problem as the function of the solutions to smaller instances of the same problem. We have seen that recursion is appropriate to be used when you can solve the original problem by identifying the solution to subproblems. This is what the recurrence relation talks about. It expresses the solution of the problem as the solution of the subproblems. For example, if you want to find the factorial, as we have discussed previously, the recurrence relation would be f of n is equal to n into f of n minus 1. Notice that this is the original problem and this over here is the subproblem, because remember n factorial is equal to n into n minus 1 factorial. Now let's take another example. We have discussed the case where you wanted to print the sequence 3, 2, 1, 1, 2, 3. What would be the recurrence relation for this? We have seen that the recursive case for that was print n and then do a recursive call for the same function and again print n. So this over here is the recurrence relation, and we have to do this when n is greater than 0. Notice that the recurrence relation actually talks about the recursive case. It does not talk about the base case, but it talks about how you can solve the original problem using the solutions to the subproblems. Once you have identified that you can solve a coding interview question using recursion, the most important step to proceed further is to be able to draw the recursion tree. You will see that if you can do that, after you're done with drawing out the recursion tree, you will be able to easily solve the question and code it out. So let's go ahead and practice drawing a simple recursion tree. Now this over here is going to be a very simple one, and we will keep drawing recursion trees as we go along with the course. So let's say you want to draw the recursion tree for the Fibonacci series. Now a quick setting of the context over here. The Fibonacci series can be defined as f of n is equal to f of n minus 1 plus f of n minus 2, and it's also given that f of 0 is 0 and f of 1 is 1. Now what does this mean? Let's write out the sequence to understand this. So the first term is 0 and the second term is 1. So let's write the two terms. Alright, now it's given over here that the next term is the sum of the previous two terms. So f of, if this is 0, this is 1, f of 2 would be f of 1 plus f of 0. And we know the values of f of 0 and f of 1, which is 0 and 1. So this value over here, which is f of 2, would be 0 plus 1, which is equal to 1. Again, the next term over here would be the sum of these two previous terms. So f of 3 would be equal to 2. Similarly, f of 4 would be 2 plus 1, which is equal to 3, and it goes on in this manner. Alright, so this is the Fibonacci series. Alright, now we will see this in a future video in detail, but over here we are just trying to try out drawing the recursion tree for this interesting question. So let's get started. Alright, so let's say we're gonna start with f of 3. Okay, so let's say we want to find the value of f of 3. So the code calls f of 3, and this over here is gonna recursively call f of 2 and f of 1. Okay, so it's gonna call f of 2, and notice that before it goes to call f of 1, this f of 2 itself will recursively call f of 1 and f of 0, right? So this is f of 1, and first it's going to call f of 1, and because we already know the value of f of 1, it's going to return the value which is 1. Okay, and then f of 2 is going to recursively call the function f of 0. Again, we already know the value of f of 0, so it's going to return 0. And now f of 2 can be calculated, which is 1 plus 0, which is 1. Therefore f of 2 is gonna return 1 to f of 3. Okay, so f of 3 is f of 2 plus f of 1. We have seen that, right? So first it will go down to this part over here. It will try to calculate f of 2. Again, f of 2 will recursively call f of 1, and because this returns, it will go to the other branch, call f of 0, get back the value, and it's done with getting back the values needed, and it will return the value 1. Now f of 3 is gonna call f of 1, and we already know that f of 1 is already computed, so it's gonna return 1. And then f of 3 is gonna return 1 plus 1, which is equal to 2. So this over here, what we've drawn out over here, is the recursion tree. Now once you are done drawing out the recursion tree, it's very easy to go ahead and code this out. Now in simple terms, the pseudocode would be just that if n is less than or equal to 1, we already know the value, right? So if n less than or equal to 1, we just need to return n itself, because for 0 the value is also 0, for 1 the value is also 1, right? And for other cases we just need to return f of n minus 1 plus f of n minus 2. Again, we are not aiming to write the detailed pseudocode over here. I'm just giving you a sample over here. We will see this in a future video in great detail, but over here we are just getting introduced to drawing a recursion tree. If you can successfully draw the recursion tree for a recursion problem, you will find that it will be a very easy task to go ahead and code it out. This is especially true for complex questions. Hey everyone, welcome back. We have discussed so far various interesting things regarding recursion. Another important thing to know about recursion is that you can write recursive solutions either going from 0 to n or n to 0. Now remember, it's interesting to know that this is possible, but if you can practice writing solutions in both ways, it's very helpful because it will help you develop a good grip on solving coding interview questions. So let's go ahead and try this out together. So let's say the question at hand is given n, find the value of 1 plus 2 plus etc. up to n. So this is the question at hand. Let's try to solve this question in both ways. We are going to do it recursively and we will do it from 0 to n as well as n to 0. First, let's write the recursive solution where we are going from 0 to n. Let's write the pseudocode for this, okay? So let's get started. Now, let's say I have a function and I call it sum, and I have the parameters, the current sum and n over here, and I'm passing the initial sum as 0 and I want to add up till 5. So 0, 5 are my inputs, and then the recursive case is that I'm just gonna return cur plus sum of cur plus 1 up to n. Okay, and again let's draw out the recursion tree for this, and the base case is gonna be that if I hit 5, right, if I reach 5, if cur is equal to n, and in this case that's 5, so if cur is equal to n, then I'm just gonna return n. So let's see if this will work. So initially I'm gonna call sum with the parameters 0 and 5, so sum 0, 5, and inside the body of the function cur at this point is 0, which is not equal to 5, so it's gonna recursively call sum of cur plus 1 and again pass n as 5. So that's sum of 1, 5, and cur at this point is 0, right? So again when we return, it's going to be 0 plus sum of 1, 5. So this sum of 0, 5 is going to recursively call sum of 1, 5, and then again we are inside the function, cur is 1, it's not equal to 5, so we're going to call recursively sum of 2, 5. This is going to recursively call sum of 3, 5, which again is going to call sum of 4, 5, and this is going to call sum of 5, 5. At this point cur is equal to n, or 5 is equal to 5, so we have said that we have hit the base or terminating condition, and let's just return n. So n is equal to 5, so this over here is gonna return 5. Okay, so this, the value of this is gonna be 4 plus 5. Okay, so sum of 4, 5 is going to give the value 9. Okay, so this over here will become 3 plus 9, which is 12. Okay, so sum of 3, 5 is going to be 12, and this is going to return 2 plus 12, which is 14. So sum of 2, 5 will be 14. 14 plus 1 is 15. So sum of 1, 5 is 15, and then we're going to add 0 to it, and thus sum of 0, 5 is gonna return the value 15. Okay, so 1 plus 2 up to 5 has the value 15. So we have solved this question using recursion, and notice that we went from 0 to n. Over here it's 0, cur is 1, 2, 3, 4 and 5, right? So we solve this question by going from 0 to n. Now let's try to solve the same question by going from n to 0. Let's write the pseudocode for it. So let's write it over here. Now I could write the function sum as sum, and the input is n, and I'm calling it with the input parameter 5, and then the recursive case could be return n plus sum of n minus 1, and the base case is if n is 0, return, just return. All right, so notice that the base case changes based on how you write it. Over here the last valid case is going to be 1, or the first invalid case is going to be 0, right? So you can think of the base case as the last valid case or the first invalid case. And in this case, because we were going from 0 to n, so 0, 1 up to 5, so we had 5 over here, which was the last valid case. So the base case changes based on how you write it. Now let's draw the recursion tree for this solution over here. So initially we call sum of 5, and this is going to call sum of 4, right? N plus sum of 4, and this is going to call sum of 3, and this over here is going to call sum of 2, which in turn will call sum of 1, which in turn will call sum of 0, and at this point we will hit our base condition and we will just return. So this is just going to return. Okay, so we could say return 0. Okay, so let's say return 0. So this value over here is going to be 1 plus 0, which is equal to 1. So this is going to be 1, and this is going to return 2 plus 1, which is 3. So S of 2 is going to be 3. Now S of 3 is going to be 3 plus 3, which is 6. S of 4 is going to be 4 plus 6, which is 10. And S of 5 is going to be 5 plus 10, which is 15. So in this way, notice that we went from 5 to 4 to 3 up to 0, or we went from n to 0. So you can write recursive solutions going from 0 to n or n to 0. So try to write at least a few questions. Try to practice writing the solution in both ways so that you get a good grip on solving coding interview questions using recursion. We have discussed various topics with respect to recursion. Remember, recursion is very, very important to ace coding interviews. Now, recursion, as we will see in the future part of this course, is in fact the parent of various other topics such as backtracking, dynamic programming, greedy algorithms, divide and conquer approaches, etc. Now, backtracking basically is just a guided form of recursion. More of that later. When it comes to dynamic programming, we will see that first we will write the recursive solution before we go ahead and build the top-down dynamic programming approach for questions. Now, the top-down approach is what is called memoization, and this also uses recursion. Now, once we have come up with this approach, we will again use the intuition that we will get from this to go ahead and build the iterative approach or the bottom-up or tabulation approach in dynamic programming. When it comes to greedy algorithms, recursion is where you try to optimize the next step. Again, we use recursion for this. In divide and conquer algorithms, again, you will see that we will use recursion to divide the problem into subproblems, and we will come up with the solution by solving each subproblem independently. So notice that recursion is a very, very important topic, and you have to master this to be able to ace coding interview questions. Also remember, if the question at hand is such that there is a tree or you're having multiple branches, for example, something like this, okay? So in this case, probably you can use recursion to solve the question. Another way of thinking about recursion is that if the question at hand is such that you can divide the original problem into similar subproblems, again consider using recursion. Let's now proceed and take a look at some interesting coding interview questions such as the Josephus problem, the Keith grammar problem, the Tower of Hanoi problem, etc. Hey there and welcome back. In this video, let's discuss how to think about the complexity analysis for recursive solutions. Let's say that for a question at hand, you are able to draw a recursive tree, and let's say it looks like this. Now, to find the time complexity, all you need to do is you need to identify the number of nodes that are there in the recursive tree, and then you need to multiply this with the work done in each node. You will see more of this in action in different videos where we discuss the time complexity of recursive solutions. So this is the general case. Now you will have some questions where, for example, leaf nodes will do some actions, but then the other nodes will do some other actions. Now in that case, you just need to identify the number of leaf nodes and multiply that with the work done in a leaf node, and then add to it the number of other nodes and multiply to this the work done in other nodes. So this will give you the time complexity in such scenarios. Now when it comes to the space complexity, and if you're only considering the recursion of the solution, then you just need to know the maximum depth of the recursion tree, because that will tell you the space used up on the recursive call stack. For example, in this case, notice that the maximum depth is equal to 3, and let's say in this particular question this is 3 because 3 is the input size, and if we call that n, the space used on the recursive call stack would be of the order of n, and the recursion tree will help you understand this because these would be the maximum number of calls which would be there on the recursive call stack at any point of time. So notice how drawing the recursion tree is extremely useful to find the time and space complexity of recursive solutions.